All right, so cross sections. We kind of came to this realization yesterday that when you slice an object, let's say we have a cube here, I want to cut through that. The shape of your cross section or the face of it is going to depend on the sides that are parallel to it. So in a cube, I can cut horizontally. So this would be my horizontal cut right here in green. And if I cut horizontally, I get a square face because the top part right here, which is parallel to my cut, is a square as well. Same thing would go if I cut vertically. We're going to show that with a rectangular prism. So if I have a rectangular prism, and let's say cut vertically. And I'll show that with the pink. Now if I cut vertically through, same process applies. The cut here is parallel to my front side and the back side. That little back side right there. Since the front and the back are rectangles, the cut's shape has to also be a rectangle as well. Diagonal shapes or diagonal cuts are different. That is entirely dependent on the shape you do. So, for example, if I decided to do a square pyramid, if I had a square pyramid and I wanted to cut diagonally through this, if you cut diagonally through a square pyramid, you would get an isosceles trapezoid. And the reason why, you're transitioning from a square cut moving into that triangle cut. My recommendation is I put a link up on the cross-section video for the GeoGebra app that I use. Mess around with that because this is so hard to just kind of see in your head. So being able to see that on the computer, at least play around with it, might help kind of make it more concrete and see where these shape relationships are coming from. But what if you were only given the cut? So for example, starting with revolutions now, we have a cylinder. And if I cut a cylinder in half, I just slice right down the middle there. I just cut this thing right in half. I get a rectangle shape. My question to you guys is that what if you were only given half of that rectangle shape? So in a 3D plane, if you were only given half of that rectangle, you would be able to spin the shape around this axis here that goes up and down to get this picture. So that's what revolutions are. A lot of the times, revolutions are just taking half of the cross section and spinning it around a 3D axis. So if you have something like this and you spun it, you would spin around to create that cylinder shape again. Let me show you guys on a GeoGebra app. So right here, just to kind of further illustrate what I'm talking about, I have the x-axis and the y-axis that we're all familiar with, but the z-axis is what creates our 3D shape. This is what determines our 3D plane. And like I said, we're given half of a cross section for a shape, just one large rectangle. And now I want to rotate this. It'll rotate all the way around that Z-axis to create that final cylinder that we're used to. So the reason why we started first with cross sections is because it kind of helps us see where this concept of revolution comes from. Two of the images build to make these 3D shapes, just like this. Now, if we were to have a cone, going back to the cone, there we go. The cylinder requires half a rectangle. A cone is a little bit harder to see. You kind of have to imagine it head on for it. So we have a rounded triangular shape around the base of a circle. But if I were to look at a cone head on, the shape you actually end up getting is a triangle. And that's proven in our cross section. If we vertically cut through a cone, we actually get a triangle shape. So we're going to apply that same reasoning to the cone. We're going to have the 3D axis with Z building a 3D image. And then you have your Y, and then you have your Z. Or your X, I apologize. That one is your X. And for the cylinder, we had half of our cross section sitting on our Z-axis. So we're going to do the same thing for the cone. Half of my cross section would be a right triangle, which means that if I were to draw this on my axis, you would just draw a triangle between the axis and the x-axis. Remember, when we're doing revolution, the idea is that you take half of the cross section and you put it on the 3D part. So now that I have that cone right there, if I were to spin that around, we would actually end up back at that 3D image. So let's try and show that again with a cone instead. So we're going to disappear with the cylinder and we go with a cone. Going all the way back here, as we did on our paper, we have half of the cross section right here. So as I start to rotate through, all those 2D images in this cross section start to build on each other. Again, we're creating a 3D image from 2D shape. That's where that idea comes from. All the 3D stuff you have around you is slowly built up in this meticulous way. So as you rotate through, you can see that cone start to appear again. Really cool. But revolutions are exclusive to these two shapes, the cylinder, the cone, but we also have it for a cylinder. I apologize, for a sphere. So if I were to look at a sphere, same concept applies. Half of the cross section of a sphere would be a half circle. So watch as it spins through. Starting at that half circle, it will build up slowly but surely to create a full sphere. So make sure we write that in our notes as well. I'll go ahead and show you guys how to write that. So again, I recommend you draw an axis in the shape at the same time. Here is my sphere. And to help make the cross section easier to see, in my little 3D dimension I gave my image way up here, I'm going to color that in just to show that that would be my cross section. And so If your cross section is a full circle, that means when we graph it, just like you saw in the app, if you graph this, you have to be graphing the half circle on it. Because again, when we spin these around, you need the half because when it rotates, it'll eventually form that full again with the cross section. So we create those axes with Z up, Y going to the left, and X going to the right. We just go ahead and graph that circle on there. Ooh, draggy. Let's graph that draggy circle on there. And then all you have to do is rotate, because again, the reason why we do the half is because as this thing rotates, it eventually will rotate back on itself to form that full cross-section image again. So you start with half, and once rotated, you'll receive that full view. We'll see that one more time in the animation. So when it goes back, so starting here, watch how it loops back. It started on that x-axis, and as soon as it crosses that x-axis, it's back to being full cross-section. Let's create some rules for ourselves before we end this. So some final rules for ourselves to keep in mind as we go through revolutions. Rules. First off, there's really only 3 3D images you can work with, and it's dependent on the base being circular or if every cross-section is circular. So things like cylinders, cones, and spheres can be made with revolutions. I'm going to do a little star below this one that says must have circle, base, slash cross section. This part is so important. Notice how we didn't have anything like a cube or, a square pyramid or pentagonal pyramid. This is what makes revolutions happen. When you spin something around, it always goes in a circular motion. So anything you're working with that you're trying to revolve around in math will typically need a circular or a curved pattern to it. Another note to ourselves for number 2. When graphed, half of the cross section, half of cross section must be on the graph. So I'm going to do it in little colors below just so we can differentiate between the notes in this part right here. If you see half of a rectangle, actually a better way to word this, if you see a rectangle graphed to be revolved, it's going to become a cylinder. And you might be thinking, well, why even bother saying the word revolve instead of saying, oh, rotate it? Rotated and revolve mean two different things in math. To rotate a rectangle, we'll still leave it as a rectangle. But revolve tells me, as somebody who's trying to solve a problem, that you're trying to rotate it around a very specific axis. So make sure when you're talking about this, you associate it with the word revolution and not rotation. Those are two different things when it comes to geometry. If you see a triangle wrapped to be revolved, you're going to get a triangle out of it. And finally, if you were to see a half circle wrapped to be revolved, you're going to receive a sphere. These are the two big rules. And you really only have a handful of shapes that you can rotate to create 3D images with. And that when you see very specific shapes graph and you're told to rotate them, you're going to get very specific shapes out of them. A revolved rectangle will get you a cylinder. A revolved triangle will get you a cone. Or, gotta make that cone, not triangle. That one is cone. And half a circle graph and revolve will be a sphere. Now, if you can combine these. So let me go ahead and move on to a couple of trickier problems that you will see in your quizzes and homework. Let's say you were given something like this. You have your 3D graph again, where you have your Y and X on the bottom with Z on the top. And let's say you see something a little funky. You first see a triangle, and then you see what looks like a rectangle below it. This is still okay. Remember, these, even though they're on two different sides, these still create two very specific shapes. When a triangle is rotated, when it's revolved around an axis, remember, that will always get you a cone. And when a rectangle is revolved around an axis, that, in turn, gets you a cylinder. So the rules still hold. You get two different 3D images when rotated and revolved around. But once you revolve them, you just get a very specific shape. It's just kind of built on each other. So if I were to rotate these two around the axis, then you would end up getting a cone on top of a cylinder. Like that. We just attach the 3D images to each other, so it's drawn that way before the revolution. That's all you have to do. You will definitely see this on your quiz, on your homework, and there will be something like this on your test, I would assume. So get comfortable with the idea of being able to work with these separately, because I searched high and low for a tool that might help you guys with these compound images, and there isn't really anything out there. So keep in mind that rules will still apply no matter what. It's just that when they're attached, that means when they're fully revolved around that axis, they'll be combined. Only difference there is the rules will still hold. You'll just get a brand new image with a cone top and a cylinder bottom. But that's essentially it for revolutions. They're not too bad. Just make sure you remember those rules as you're working through it. I recommend maybe playing around with a couple on your own. If you guys would like more help with this or extra practice, let me know and I'm more than happy to post more. And that is it for today. All right, guys, I hope you have a fantastic rest of your day.